So at this point, we've solved this MOSFET amplifier for the various characteristics as in the textbook, the gain, output resistance, and the loop gain. And so we've basically just verified what was done in the textbook for this example. The number depends on what version you have. But now we're going to go further, because as interesting as this is a DC, what is truly important with feedback amplifiers in designing them is their stability properties. And to understand the stability properties, then we really have to account for the parasitic capacitances that exist in any practical circuit. Okay, so parasitic capacitances are basically appear at every node, and there are others as well, but let's just think about the capacitances at each of the circuit nodes. So here, so let's call it capacitor C1, another one at the output, capacitor C2, and then there's one on the source, capacitor C3. Okay, so each of these capacitors will result in some delay, and as we increase the delay, then the feedback starts to have trouble and we run into stability problems. So we want to analyze the stability, and the key, as you've studied in control systems and maybe the circuits courses, the key is to understand the loop gain. Okay, so the loop gain we've looked at before is just this path. So here, this is the loop gain, and we can say loop gain is basically C, D, E, F, G, H. E, F, G, and H. All right, now what happens then when we add the capacitances? Well, each of the nodes then has an additional element to ground, and that intuitively would affect the driving point impedance of each of these nodes. So the driving point impedance of VD1 would be E. So rather than just being RD1 as before, now C1 will also appear in parallel. So there will be in parallel 1 over SC1 in the S domain. Okay, similar for the output, the driving point impedance before was RD2 in parallel with R2. So there's going to be capacitance now in addition to that, 1 over SC2. And then finally over here, there used to be just R1 in parallel with R2. This 1 over GM came about from the GM1 of Q1. And so now we're going to add 1 over SC3. Okay, so it's simple enough to account for the capacitances, and you can see that our loop gain will now become a function of S. And even though it looks complicated, when we're looking at the loop gain, we can see then it's really just affecting the driving point impedances. So basically C, E, and G. Okay? And so if we look at each of the terms, then let's start with, because I know the significant capacitances will be C1 and C2, followed by C3. So let's just go through each one. So capacitor C1 then is added to E. So our E is, it used to be simply RD1, but now it's going to become RD1 in parallel with R1 over SC1. And when we have the addition of a capacitor to a resistor, so here, if we had a resistor here, and then we added a capacitor, 1 over SC, well then the combination of the two in parallel would be simply 1 over the conductance, so that's 1 over R, and we have to add the conductances together, or admittances, so SC. And so you can see then the equivalent impedance becomes multiplied by R on the top and bottom, and you get 1 plus SRC. Okay, so what used to be simply R, we have a new term in the denominator of 1 over SRC. And a reminder that the SRC we can also write as S over omega P, where omega P is equal to 1 over RC from EC 212. Okay, so we're adding all of these capacitors in parallel. So E, for instance, becomes now here. So let me just write this down here. So E becomes, used to be RD, but then we simply add the denominator. So RD1 is now RD1 over S over omega. Let's call this P omega P1, where, as we said, omega P1 is just the product, 1 over the product of the resistance, which is RD1, times the capacitance. Okay. So similarly, for G, I guess I can just set it to equal. This is now RD2 in parallel with R2, parallel with 1 over SC2. So we can see that we can rewrite it as simply the original impedance. So RD2 in parallel with R2, and it's going to be 1 over S omega P2, where omega P2 is, as we said, the resistance, the product of the resistance, or 1 over the product of the resistance, which is RD2 in parallel with R2, multiplied by the capacitance, C2. Okay. And then finally, for E, we've got G and now C. That is going to be what it used to be. So R1 in parallel with R2 in parallel with 1 over GM1. And I guess I'll just save the expression that, and we're going to, well, now I'll just say that 1 over 1 plus S over omega P3, where omega P3 is the product, 1 over the product of the original resistance, So R1 in parallel with R2, parallel with 1 over GN1, and multiplied by the capacitance C3. And unfortunately, it's this letter is C from the signal flow graph, not C, the capacitor. Okay, so we basically have now the expressions for the three poles, and because the loop gain is simply a product of all of those terms, then the loop gain will remain what it used to be, except now we're introducing these three denominator terms. And so the loop gain, what I'll say is it'll be the loop gain, the original loop gain, which was at DC and it had no capacitors. So we could just call that loop gain L0, say. And then we're going to add the denominators here. 1 over omega P1, 1 over, S over omega P2, and 1 plus S over omega P3. Again, this is just the loop gain because we're simply multiplying that out, and these are the new terms that are introduced. So now we have the loop gain. It is a function of the frequency S, so it's L of S now. And the DC gain, loop gain, DC values we said before, we calculated was, this is 16.35, and then it drops. So you can see it's a third order response, and now we have actually algebraic expressions to determine the pole frequencies. All right, so let's try to put in some preliminary values. So here I'll put just an initial set of values and see how that turns out. So let's use, I placed 10 picofarads. So 10 picofarads, 5 picofarads, and 1 picofarad here. Okay, so if we put that in, and we'll simulate this, so 10, 5, and 1 picofarad, then the transient response looks like this, and we can see that we have this underdamped response to a 300 nanosecond pulse. Okay, so that shows us it's underdamped, and we know that there's some stability issue if we don't want an underdamped response. We can now think about the actual locations of the poles, and we can see using the expressions and the values of the circuit elements, then the first pole is at 10 megaradians, then 4 megaradians for the second pole, and the third pole is way up at 510, times 10 to the 7 radians. So you can see 1, 4, 510, that's really this, we can ignore, this is at such a high frequencies, we can ignore that, so it's helpful to know, and you don't have to consider C3, so we'll think more about C1, C2, and omega P1 and P2. And we can see then that here's the loop gain. If we plot the loop gain, it's Bode plot, so it's magnitude plot here and the phase plot, then this is typical Bode plot from second year. You can see that with a gain of 16.35, then it's 24 dB, and the first pole comes in at 10 megaradians, but then pretty soon, at 40 megaradians, it comes the second pole. So we know this first pole gives us a first order drop off. So if this is at 16, gain of 16, then we know then that since it's only a factor of 4 down, then the gain here would be about a factor of 4 down from here. So the gain is 4 around here, which would be about 12 dB, certainly above 0. So that's a problem, because once we hit the second pole, if the gain is above 0 dB, the gain, there's still a distance before we reach 0 dB, and you can see then that that second pole accounts for the drop past minus 90 degrees. So that's going to result in a relatively small phase margin. Nyquist's stability criteria tells us that for a feedback system to be stable, then when it reaches 0 dB, then the phase cannot be, in order to be stable, it can't reach 180. So here we are pretty close visually. You can see it's pretty close to 180, and so the phase margin, which indicates the margin away from instability, is quite small. And so we know then that that's the reason behind this underdamped response. So what can we do then? Well, we have expressions for the pole frequencies, and so we can do one of two things. We can do a number of things, but let's just concentrate on the values of C1 and C2. What can we do to affect an improved phase margin? Okay, so there's basically two approaches. One approach would be if we try to decrease C2 and thereby increase omega P2, the second pole. So I've tried to show this over here. And what you see is by decreasing C2, so from 5 picofarads down to 1 picofarad now. So we've dropped C2 by a factor of 5. That's going to increase the pole frequency by a factor of 5. So it goes from 40 megaradians to 200 megaradians per second. So this is going to move omega P2. So from here, then we end up with the purple plot. So moving this over here means that it will affect the phase. You can see how the phase of minus 90 degrees now extends out into a higher frequency than before. And only when we reach to omega P2 does it drop significantly. And so compared to the original curve in green with the small phase margin, by increasing omega P2, this purple line, the unity gain frequency has now, at this unity gain frequency, we can see that the phase has extended out higher. So now the phase margin taken at the unity gain frequency is larger than before. Okay? And that's one way we can solve it. The other solution or possibility is, what if we decided to increase C1 and thereby decrease omega P1? So we'll leave omega P2 and P3 alone. So they are in the same locations as before, but now omega P1 has moved from here down below. We do this by increasing C1, and so if we increase it by a factor of 5 from 10 picofarads to 50 picofarads, then we will decrease the first pole from 1 or 10 megaradians to 0.2 or 2 megaradians per second, and so it moves from here down to here. What that does is it decreases the gain. So because it starts to drop at a lower frequency, then it reaches 0 dB at a lower frequency than before. So our unity gain frequency has gone from here to here, and you can see then dropping the first pole causes it to reach minus 90 degrees sooner, but then because the higher pole frequencies are unchanged, then the phase response at higher frequencies stays the same. Nonetheless, we've moved the unity gain frequency, so we read it off, instead of reading it off here, we read it off now in this purple line at this point. So we go down here, and we can see then, because the phase hasn't changed, but the gain has changed, then we end up with a higher phase margin. Okay, so either we can take two tacks, either decreasing C2 or increasing C1, and you can see from the simulations that compared that both solutions are possible, and we can compare the response with the original plot. So you can see that this underdamped response is gone more towards a less underdamped or maybe critically damped response. So there's less ringing. In this case, decreasing C2 is nice. This would correspond to, if you recall, C2 is at the output. So that would imply that if we could reduce the load capacitance on the amplifier, then we'd reduce the ringing, and it would still be the same response, relatively a fast response. Sometimes, however, the capacitance at the output is constrained, fixed. Say if you were selling this as a component and you guaranteed that the amplifier could drive a load up to 5 picofarad, then you have to keep this, in which case your design freedom as a designer would be to increase capacitor C1. You're keeping this fixed. Increasing capacitor C1, as you can see, in comparison, this is a slower response, so it takes a longer time to settle, but nonetheless, it still settles within the 300 nanoseconds that we've given it. It just takes a bit longer than this one. But still, it satisfies the requirement, and it's a trade-off then between response time and stability. So one of the many typical trade-offs that we have as designers. So to recap then, this set of videos has gone through the analysis of a typical transistor feedback amplifier using signal flow graphs. We've shown how to take a circuit and convert it to a signal flow graph. We've shown you how the signal flow graph can be used to analyze the circuit, and this current video we've talked about how we can analyze the stability and to obtain a set of useful expressions that would allow us to identify how the different element values affect the pole locations and hence the stability of the amplifier. This was all done with hand calculations and hand-drawn graphs. The purpose of the capstone project is to develop a CAD tool which can automate much of this process. So that includes taking the schematic from SPICE and then automatically generating the signal flow graph, the ability to switch or toggle between the symbolic expressions and the numeric values, the ability to determine expressions for the loop gain, as well as to plot the loop gain as a bode plot, and the ability to change values in order to see how the values affect the loop gain and stability properties. This current iteration of the project will look at the last key component, which is the ability to simplify the signal flow graph as we've done in this example. Simplifying the signal flow graph is key in coming up with expressions, algebraic expressions that are simple enough that we can use as designers to guide us in our design of the